Okay, so very pleased to welcome Lorenzo, who's waved his hand and is going to talk about the Goeritz matrix, I think.
Yep.
Excellent. Okay.
So let's see. Here and so do you see a piece of paper with the phrase Goeritz matrices at the top?
We do indeed.
Okay, good. Okay, and I do see your faces at the side. Very nice. So I'm going to start with some thank yous to some co-authors. I spent 2016, 17, and 18 thinking about some of these things, and a lot of that time I was talking with Bill Watkins and Derek Smith about algebra associated with the Laplacians of graphs. And I also spent some time in there talking with Dan Silver and Sue Williams about the Dane presentation of linked groups and its connection with the Goeritz matrix. So all of that was very illuminating. And thank you to Roger and Lou in absentia for running the seminar. It's been a real pleasure to participate, and it's an honor to be asked to present. Okay, so let's see if we can get to the content here. So this is one of the oldest ideas in knot theory, that there are two checkerboard shadings. They're just opposites of each other of a knot diagram. I use the letter sigma to represent a shading, and I have an index indicating the status of the unbounded region. So with the subindex U, it's unshaded, and with the subindex S, it's shaded. And different people have different preferences. I have no preference. So I allow them both. I consider them both. Goeritz's idea was to associate an index to each crossing with respect to a shading. I think of the index by standing here in an unshaded region and looking toward the crossing. And if I see the overpassing arc on my right, then it's a positive crossing by this scheme. If I see the overpassing crossing on the left, it's a negative crossing. Okay. Again, that'll be the opposite if you look from a shaded region. Or to say the same thing a different way, if you flip your shading convention, then the index will flip sign for each crossing. Okay, and just to make the obvious remark here that the Goeritz shading reflects our sense of the orientation of the plane, but not the orientation of the knot or link in the diagram. There are no arrows in the diagram, but there is a distinction between left and right. So we make a symmetric matrix using these indices, and the convention I'm going to follow is that the off-diagonal entry of the matrix has the negatives of the indices of crossings involving the two unshaded regions with those indices, and then the positive index values are on the diagonal of the matrix. So you have a symmetric matrix whose row and column sums equal 0. So here, for instance, is a right-handed trefoil. We stand here and look toward this crossing. We see the overpasser on the right. Maybe that's unnatural. Maybe we stand here and look toward the crossing and the overpasser is on the right. That means the index is +1. The indices are all the same. There are two unshaded regions. So first one and the second one, 3 crossings between them, all of positive index. So they give you negative off-diagonal entries and positive on-diagonal entries.
What are the row and column indices of the matrix? Are they the unshaded regions?
The unshaded regions, that's right. That's why this one has 2 and this one has 3. This picture of the same knot, the opposite shading, has 3 unshaded regions. And you can see this time, if you stand in an unshaded region and look toward a crossing, the overpasser is on your left. So these are all negative crossings by this scheme. Off diagonal entries are +1, one crossing between each pair of regions. And then the on diagonal entries are just inserted to cancel. So the row and column are 0.
And the numbers just tell you how many other regions are shared? The ijth entry, the absolute value.
ijth entry is just one index comes from one of the regions and the other one comes from the other region. So we are indexing the unshaded regions and using that for the, so it doesn't matter since this is a very symmetric diagram, but let's say this is the first region here, then its crossings with other regions correspond to the off diagonal entries in the first row and column. Those are the same because the matrix is symmetric, and then they're totaled up on the diagonal with a minus. Okay. As you can see in either of these matrices, the codimension 1 determinants have absolute value 3. Here, that's the entries. Here, it's the 2 by 2 submatrices. Okay, you get 4 minus 1 or 1 plus 2. Either way, you get 3 for the determinant. Okay. We'll get back to that. So two obvious properties of these matrices reflect what Reidemeister called the omega 4 and omega 5 moves. The omega 4 move is removing a nugatory crossing, one of everybody's favorite words in knot theory, the nugatory crossing. And you can see here that this nugatory crossing in the middle is removed by simply picking up this entire right-hand portion and rotating it through 180 degrees across a horizontal axis here. And I mentioned that so you can trace it and notice that the index of the crossings is unchanged by that rotation. Okay, the eta values stay the same. So for instance, this crossing here, when you look at it from the unshaded region, the overpasser is on the right. Its image is over here when it's flipped. When you look at it from an unshaded region, the overpasser is still on the right. Okay, so the matrix ignores this crossing. If you look at the definition, the only crossings that enter into the matrix are crossings between different regions. So this crossing is totally ignored in the matrix. And what I'm saying here is the matrix is being smart to ignore this crossing. The crossing doesn't contribute any real information. Okay? The other thing you'll notice in the definition is, I don't know if I wrote down the formula, but it's this word sum, that the indices are added together. So obviously if you have positive and negative crossings, they're going to cancel. This also is smart. So it's a smart matrix, good matrix. If you have opposite crossings between the same two unshaded regions, then there have to be an opposite pair that are consecutive in the sense that as you walk around one region's boundary, they are opposite crossings that are consecutive between those two regions. That's this region here and this region here. There could be other stuff intervening, but they're consecutive as far as those two regions are concerned. And this is what Reidemeister called an omega 5 move, is taking this whole portion of the diagram and just flipping it over. And that'll remove those two crossings. So once again, the matrix is smart to cancel those two because they don't contribute anything. They can be canceled in the diagram. Or just to say again, that the traditional discussions, usually for specificity, a person specifies whether they like the unbounded region to be shaded or unshaded. You can do that if you want, I don't care. I don't do it, and it makes no difference because if you insist on having things one way, I can always replicate that with the opposite convention with a different diagram by using stereographic projection to change which region is the unbounded. Okay, so here I've taken, I guess it's this limb of the trefoil diagram, thrown it across the point at infinity and brought it back. And the result is to open up this shaded region to include the new point at infinity. The diagrams look very different, but notice this region and this region are the two unshaded regions. This region and this region are the two unshaded regions. And there's a clear correspondence between the crossings that connect. Okay, so the matrices are clearly identical. Okay. So I'm going to let script G of a knot. Oh, by the way, I'm just talking about knots at the beginning of the talk, not links. So strict knots, one component. I'm going to let script G of a knot be the set of all Goeritz matrices that you get from different diagrams. Obviously, there's a question here. It's a question that Goeritz raised. How are the different matrices related to each other? And I'll get to that. There's not a good answer. So this script G of a knot is the collection of all Goeritz matrices of that knot. On the face of it, it seems possible that you could have three knots so that you get from the first one to the second one through a sequence of Reidemeister moves and then a switch where that switch preserves the Goeritz matrix. And then in the second one, K2, you could do some other Reidemeister moves and have another switch to a third knot that preserves the Goeritz matrix. On the face of it, it seems possible that you wouldn't be able to go directly from the first knot to the third knot. So when you talk about equality of Goeritz matrices, it's not clear that it's a transitive relation. And so in order to provide an equivalence relation, I'm going to say two knot types are Goeritz equivalent if you can get from one to another through a sequence of knot type preserving moves and moves where you switch from one knot to another with the same Goeritz matrix. I'm going to call that Goeritz equivalence. I don't know if that terminology has been introduced before, but that's the terminology I use. Okay, so we have an equivalence relation from the Goeritz matrix, and now it seems appropriate with the British part of the audience to say, and now for something completely different. And so I'm going to talk about elementary mutations for a second. There are three types of elementary mutations. You have a portion of a knot diagram with four strands connecting the interior of the disk to the exterior of the disk in the diagram. The three types of elementary mutations involve rotations through an angle of 180 degrees across various axes. This first one you can see is across this axis. No. It's this axis here, right? So the thing is being flipped this way. This diagram here, I can't see it because of the faces. This one is that the, so this one was this way, this one is this way, right? Across the vertical axis. And this one you'll notice is the composition of those first two. So if I first go from here to here and then perform this flip of left and right from over here, I'll go from here to here. Okay? So two, I can think of it as two basic ones and then their composition. And I'm going to say that two knots related through Reidemeister moves and elementary mutations are Conway equivalent, even though if I understand the history of this correctly, the notion of mutation, not the word, but the notion, is actually older than Conway's work, but certainly became part of the common terminology of knot theory when Conway talked about it. The surprising theorem that I want to start off with is that Conway equivalence is exactly the same as Goeritz equivalence. Okay, so the equivalence relation you get on knot types from equality of Goeritz matrices is exactly the same as the equivalence relation generated by elementary mutation. And so an equivalent thing to say is that if you could precisely describe the effects of Reidemeister moves on Goeritz matrices, you would have precisely described what it means for two knots to be mutants of each other. The proof of this is very easy. I'll start off with this direction, which is what if they're Conway equivalent, they're also Goeritz equivalent. Remember that both equivalence relations include Reidemeister moves. So all I have to talk about for this is the elementary mutations. And this is it's this proof that is the reason I don't have a preference with regard to which shading to use, because I like to be able to switch between them. So if I'm performing this elementary mutation, if I shade it this way, so look at the information you have about incidences between unshaded regions in these two diagrams. Naturally, this unshaded region corresponds to this one here. And this unshaded region corresponds to this one here. And whatever incidences there are going in here are simply flipped upside down going in this way on this diagram. But you'll see the same incidence information on the unshaded regions, passing from right to left in this diagram, if you're standing on your head, as you would see in this one if you're standing on your feet and passing from right to left. Okay? So we're going to get exactly the same matrix up to permutations of the rows and columns, which we don't care. For the second type of elementary mutation, we have exactly the same process, except we put the unshaded regions on the top and bottom. If we walk through the diagram from bottom to top here, we'll see exactly the same information about incidences of unshaded regions as we'll see here, except for this, we would be facing into the plane, and for this, we'd be facing out of the plane. So our left, what we see on our left in this picture is what we see on our right in this picture. But you'll get exactly the same matrix. The third type of elementary mutation is just the composition of these first two. So you perform one of them, flip the shading, perform the other one, and you will have a sequence leading from the beginning to the end of the mutation involving a change that preserves the Goeritz matrix, a change of Reidemeister moves that accomplishes the switch of shading, and then another change that preserves the Goeritz. Okay. And so that's the entire first direction of the if and only if. For the second direction, I'm going to reference the theory of planar graphs. So the information that's recorded in the Goeritz matrix is the same as the adjacency information in one of the checkerboard graphs that you would build with a vertex for each unshaded region and signed edges between them for the crossings, with the edges carrying the Goeritz index as a sign. As I said before, there's a certain amount of simplification because of, for instance, the cancellation between positive and negative crossings, but that would still be a checkerboard graph for a simplified diagram, as I indicated earlier. So the Goeritz matrix carries the same information as a signed checkerboard graph. And when you have two diagrams with equal Goeritz matrices, the two corresponding graphs are isomorphic to each other in the abstract. There's a correspondence between their vertices that precisely matches adjacency information, including the signs of the edges. And so to compare them, we need to reference the theory of planar graphs. And it just turns out that if you look things up, then the different plane embeddings of isomorphic graphs are connected to each other through very simple moves, which can be expressed in terms of either Reidemeister moves or elementary mutations.
Doesn't the Reidemeister 3 move and introduce a star triangle relation on the underlying graph?
Yes, it does. And remember that both equivalence relations that I'm talking about simply allow Reidemeister move. So I'm not talking in detail in this argument about the effect of the Reidemeister moves. I'm talking about what relation you get if you take the Reidemeister moves as given and you add to them, on the one hand, the elementary mutation moves, and on the other hand, moves that allow you to re-embed equal or isomorphic Goeritz matrices, isomorphic checkerboard graphs. Okay, so the cute thing about this argument is that we're just totally sidestepping what effect the Reidemeister moves have on the graphs, because those are incorporated in both equivalence relations. Is that okay, Scott?
Yeah, okay.
Okay. So I'm not going to give you details of this argument. I wrote it up and took a long time, deciding on the prettiest pictures. As far as I know, the first person to notice this was Lipson. This was in 1990. So this was only a couple of years after Thistlethwaite's theorem. So Thistlethwaite's theorem connected the checkerboard graph to the Jones polynomial through the Tutt polynomial, which is a graph invariant. And I'm guessing that Lipson was thinking about that. And what he proved in this paper was that the Goeritz matrix determines the Kaufman polynomial. Okay, so he was thinking of invariants of unoriented links and knots that are invariant under mutation. So he presented this argument as part of that. And what I'm observing here is that the argument is a little more useful than he thought. You don't need to have the Kaufman polynomial as part of the conversation. Several authors have rediscovered it and used it for slightly different purposes, but I won't go over that. Okay, so this is the theorem, and I was kind of startled to realize this, that equality of Goeritz matrices defines the same equivalence relation on knot types as mutation does. Once again, so let me stress, that means that if we could understand the effect of Reidemeister moves on Goeritz matrices, we would immediately understand the significance of mutation for knots. And now I'm going to mention two examples that were found by Stoimino. I'm amazed by this work of Stoimino's, just the amount of extremely intelligent use of computers and invariants in this work of his. Remarkable results. At any rate, these particular knots, oh, I forgot to highlight this arc here, sorry. These two examples are clearly mutants. The part above there is just flipped from left to right. And what Stoimino said about these two, you can count up, these two diagrams have 15 crossings apiece. What he found is that each of these two knots has a 14 crossing diagram. And he could determine that the 14 crossing diagrams are unique. That each of them has only one 14 crossing diagram, and neither of them has any visible opportunity for mutation. So those properties of these two knot types there's no non-trivial opportunity for mutation. You could always take a crossing and flip it through 180 degrees, which has no effect. Now you can look at these. These are related through this kind of elementary mutation, which remember preserves one of the Goeritz matrices. So these two are knot types that have an identical Goeritz matrix with 15 crossings, but have Goeritz matrices with 14 crossings that cannot be identical. Because if they were identical, there would be a string of mutations leading from one to the other at the level of the 14 crossing diagram. So what that means, oh, I forgot to put the citation. What that means is that for these two knot types, the sets of Goeritz matrices have a non-empty intersection, but they're not the same set. And what that means about the Goeritz matrix is that you cannot determine the effects of the Reidemeister moves on a Goeritz matrix just by looking at that one matrix. So this is a surprising negative result. Certainly Goeritz didn't know this. I don't think anybody who studied Goeritz matrices realized this, that it is impossible to look at one Goeritz matrix of a knot and determine from that all the other Goeritz matrices of the same knot. It's a very discouraging observation. And it's an indication that you need more information to determine all the Goeritz matrices of a knot type than just one Goeritz matrix. It would be interesting to think about what kind of information you could use to supplement and whether it's a convenient way to describe mutation. So ideally, you could find some supplementary information that would allow you to determine the entire set of Goeritz matrices of a knot type. Then you would have two sets of matrices that are identical for two knot types, if and only if the knot types are mutant. So that's an open problem. I would love somebody to solve that. Okay, so that was all about knots. The reason I restricted that to knots is that links are a little more complicated. So there are two adjustments we make for links. The first adjustment is if the surface that comes from the shaded regions is disconnected, then we adjust the Goeritz matrix just by packing in a bunch of zeros here to increase the size of the Goeritz matrix to reflect the disconnectedness of the surface or graph that comes from the shaded regions. And the reason you need to do that is just that you really do need to do it. So for instance, these three unlinked diagrams would have the same Goeritz matrix if you didn't do that. You see there's one unshaded region. And with this adjustment, you would augment the size here with 2 extra rows and columns of zeros, augment the size here with 3 extra rows and columns of zeros. And that would allow you to know how many components there were in the link. So it's a very simple adjustment. This adjustment goes back to Murasugi's work on the signature in the 1960s. The second adjustment involves taking the orientation into account. A knot has only 2 orientations, so you can do most of the work of knot theory for strict knots without paying attention to the orientations, and then you just have 2 choices at the end. For links, there are 2 to the number of components choices of orientations. That's a lot of information, so you don't want to just ignore that. And the way I suggest incorporating that into the Goeritz matrix is to change your definition of the matrix so that each crossing's tag incorporates both the Reid and the Goeritz index. Then you have an oriented version of the Goeritz matrix. And the earlier theory just carries through perfectly. So as long as you have a Goeritz matrix that is adjusted in these two ways to incorporate this block of zeros for the disconnected shaded diagram and the rive for the orientations, the whole theory carries through, and you have a matrix invariant with the property that two oriented links are related through mutation if and only if they're related through moves that allow you to replace one link with another one if it has an equal Goeritz matrix, an oriented Goeritz matrix. Okay, so remember we can't, I guess I should ask if there's any comment about that.
Sorry, you didn't give any details for that adjustment.
So again, the adjustment is simply, so for instance, you could replace the index of each crossing with an ordered pair of the Goeritz index and the rive.
Oh.
And just incorporate that into a matrix in the same way that there is a row and column for each unshaded region, and the off-diagonal entries are the formal sums of the ordered pairs for the crossings between those two regions.
So, but the rive, I don't understand what you mean by the rive.
Just the ordinary rive that the right-handed crossings are +1 and the left-handed crossings are -1.
Oh, okay. That's between the two components.
Between the two strands at a crossing. So I'm thinking of what I mean is the local rive of that crossing.
Right. Okay.
I just combine that with the Goeritz index as an index for that one crossing, and I tabulate all of that information in a matrix. So I'm, a more careful treatment of this would involve checking some details. You may remember that for mutation of oriented links, you have the possibility that the orientations of the strings inside the disk of the mutation have to all be reversed. That's a possibility. Since the rive of a crossing is determined locally, reversing all those orientations will not change the rives inside the mutation disk. So that's the reason the matrix is preserved. Okay. Once again here, if I go to a picture of a mutation here, it's possible when you do the mutation that the orientations didn't match, so that when you do this reconnecting, the arrows are at loggerheads. And then you would have to reverse all the orientations within the mutation disk. But that won't have any effect on the rives, because they're all the crossings either have no orientation reversal or both strands orientation reversal, and the rive stays the same. So the matrix that you would get is preserved by the version of mutation that's appropriate for oriented links. Is that okay? And the way you justify the assertion that the machinery all carries through is simply you do it to the unoriented links underlying the oriented links, and then you reimpose the orientations and check that that can be carried through the mutations. So you have a matrix formulation of the idea of mutation. Again, I don't know yet of any way to make use of this, but it does provide you with the opportunity to try to use this matrix as a guide to detecting mutation of links. Okay, so for 10 minutes, I'll tell you about the older theory. So remember, it's futile to try to precisely describe the effects of the Reidemeister moves on the Goeritz matrix, either in the oriented case or in the unoriented case. Although you can't describe them precisely, you can do better than just throwing your hands up in the air and saying, I give up. The basic idea of this comes from Gordon and Litherland in '78. You notice, by the way, that's 45 years after Goeritz's initial introduction of the matrix. And their idea requires that you work with an oriented link. There are two ways that an oriented, a crossing in an oriented link can be positioned with regard to the two surfaces. So they call this type 1 and this type 2. You can correct a Goeritz matrix by, here's the ordinary Goeritz matrix. Here is that block of zeros we were going to put in. And here, this A matrix is a diagonal block that comes only from these crossings and reflects the negatives of their Goeritz indices down the diagonal. So it's a diagonal matrix with an entry for each of these crossings with only a diagonal entry, and that equal to the negative of the Goeritz index. And what Gordon and Litherland did was they used the sum of these as a correction term for the signature. And a couple of years later, I noticed that the matrix you get actually has a strong invariance property, namely that it's invariant under two moves, one of which involves the adjunction of this diagonal block here, and one of which involves what's called congruence over the integers. I didn't mention it before. This congruence coming into the theory goes back to Goeritz. It's the reason that Goeritz thought the quadratic form was important is because this is the classic number theory expression of the quadratic form with the invariance under integral congruence. This is a cute theorem. The signature is invariant because these two terms would cancel in the signature, and signature is invariant under unimodular congruence. The determinant, if you multiply by the square root of -1, the determinant of the submatrix that you get by removing the first row and column of that H block there, that determinant will be invariant. And of course, the elementary ideals will be invariant. So I point out here that the signature and the sign diversion of the determinant, the invariance of these didn't become known until the 1960s, 1970s. So before that, knot theory tended to focus on invariance like the absolute value of the determinant with a plus or minus. And I often think it would have been interesting if somebody had found this earlier, because it was a basic observation in the development of, for instance, of the Conway polynomial. Just as a simple application, I think this is the easiest way to distinguish the left and right-hand trefoils. You may remember that in the 40s, Fox published a note distinguishing the left and right-hand trefoils using the peripheral structure of the fundamental group, which is a lot of machinery. If you look at the Goeritz matrix here with the adjustment, when you orient this, you see when you come around, both arrows would be pointing into this crossing from this region. That makes this type 2 crossing. All of them are type 2s, so you get the negatives of their indices trailing down there. You may remember from college linear algebra how to calculate a signature. You use paired row and column operations to diagonalize. Then you ignore the 0, and you have the number of positive entries minus the number of negative entries. So you get -2 for the signature of the right-hand trefoil. You can use the other shading, you get the same result. This time the crossings are all type 1, so there's no extra diagonal stuff here. Use paired row and column operations to eliminate entries. You get 2 negative ones, so 2 negative entries, not 2 negative ones. Signature is still -2. You do it on the left-hand trefoil, you're going to get signature of +2. So they are different knot types. I think we mentioned earlier in this series how hard it is to explicitly use quandles to distinguish the granny and square knots. If you take the connected sum, the signatures add. So one of them has non-zero signature, and the other one has signature 0. It's a very easy way to distinguish. The Goeritz matrix also serves as a presentation matrix for an abelian group, which is associated with the first homology group, the twofold cyclic cover. I say associated with because some people call the Goeritz matrix the matrix you get by stripping away that first row and column. That'll change the group, but in a fairly trivial way. It removes a direct sum and isomorphic to the integers. To say the same thing in a simple way, Scott, the group you get from the Goeritz matrix is the same as the group you get by simplifying the Alexander module by setting the variable of the Alexander polynomial equal to -1. And that's the connection with colorings for the Goeritz matrix. So the t goes to -1 is the signal of the Fox colorings. And so the Goeritz matrix is connected with the Fox coloring. This is an observation that I think if Ken were here, he would tell us that the observation goes back to Reidemeister. I haven't independently verified that. That would be the interesting observation that the Fox colorings go back earlier in time than Fox. So just to comment here, these are useful invariants, certainly. And it's well known that they're mutation invariants. They're not classifying invariants because they don't detect the Goeritz matrix. Precisely, they're just invariants of it. Okay, so just to stress again, the variation of the Goeritz matrices under the Reidemeister moves is not precisely understood. It cannot be precisely described using information from just one Goeritz. But as an example, the connected sum of these two pretzel knots can't be distinguished from the unknot by this machinery of mine from 1984. They can't be mutants because one of them is an unknot and the other one isn't. So the theorem is not precisely detecting the Goeritz matrix. Just to say here that in closing that there's a lot of interest in region-based invariants. I haven't surveyed that at all here. This is a list of some of the references I've looked through in recent years, and apologies to anybody whose work that I've left out. These are just some examples. It would be interesting to see a detailed, unified view. There's a nice chapter on some of these matters that Shatitsky wrote 4 or 5 years ago. But there were, things left out of it. And obviously, as in all of math, there's a lot of research going on right now. That's it. Thank you for your attention. And just to say, always happy to have any comments that anybody might have now or in the future. Drop me a line. I'm glad to talk about this.
Do you want to stop sharing?
Sure. Do I know how to do that? I have to go over to Zoom.
There's a...
All I've got, stop share on the top.
Yeah, that's brilliant. Okay.
Thank you for your attention.
Well, thanks very much. That was very interesting, Lorenzo. Things I didn't know about. I mean, sort of vaguely knew about the Goeritz matrix, but all the other, you know, how it's related to mutants and things. It's yeah.
Yeah. Well, one thing that's happened, I think, is that the checkerboard graph is of interest also in virtual knot theory.
Mm.
And like all of classical knot theory, it weakens when it moves over to virtual knot theory.
Yeah.
And one of the things I wanted to stress is that there's still strong, important questions to be answered in classical knot theory about the significance of the checkerboard.
Good.
So, do you have any comments on that, Lou?
Other than to agree, no.
Okay. Right. Well, any other comments?
I have a question. Thank you for your talk. I have a question. In one page of your slides, you give the main theorem of Gordon and Litherland. Yeah. The A item, you have a submatrix 1, 0, 0, minus 1. Yeah. But I remember that in Gordon and Litherland's paper, it is not 1, 0, 0, minus 1. It's just minus 1.
Sure. So what do I do? Share this again? So let's see if I can find the statement of the theorem you were talking about. So there are two results, and I may have gone too quickly here.
Yeah, this page.
So here's the matrix, and the A thing is in the middle here. I talked about the B first, but at any rate, the A is a diagonal matrix that has an entry for each type 2 crossing equal to the negative of the Goeritz index of that crossing. So the A submatrix here will not have pairs of one.
Sorry, not this A, the next page,
Right.
Yeah,
So
this A, this little a, yeah, here.
The invariance result for the matrix has this as a correction term.
But I remember the correction is not a 100 minus 1, it's just minus 1.
Yes, they mentioned that, and that's actually it's plus or minus 1. That's the traditional Goeritz formulation. If you look at Goeritz's original paper, he has plus or minus x sub n plus 1 squared, I think, which is the way you would express that in the language of quadratic forms. And this is a sharpening of that.
Okay.
This is my own theorem.
Okay.
This is a sharpening of that. The improvement, first of all, maintains the signature because those two terms would cancel in the signature. And second of all, allows you to obtain a determinant that's well defined, including the sign.
Yeah.
Not just the absolute.
Yes. Now the signature is an invariant.
Exactly.
If
So
there starts the minus 1, it's not invariant. Okay.
So the Gordon and Litherland formulation, what they did was they talked only about the original Goeritz matrix and then used the entry sum of this block as a correction term for the signature.
Yeah.
Okay. And so what I noticed was that if you took the correction term and incorporated it in the matrix, you would get a matrix with a finer invariance result. By the way, for those of you who are interested in quadratic forms, this block here, this looks kind of innocuous if you're a naive person like me who doesn't know much number theory. But this is actually extremely destructive in number theory. The block here, the introducing of basis elements whose inner product with themselves are plus or minus 1, even just introducing one of them has the effect of splatting the quadratic form. So you have a lot of quadratic forms that are inequivalent that become equivalent when you adjoin just a single diagonal entry of plus or minus.
Yes, yes.
So in the theory of quadratic forms, for instance, the interesting part of the theory is the binary quadratic form, the 2 by 2. And when you embed them in the 3 by 3s, you lose a lot of details. So I should go back to stop sharing. Thank you for the question, Barry.
I have some work closely related with the Gordon and Netherlands paper, so I'm familiar with that paper. May I have your slides or email?
Certainly. You can just Google my name and get my email.
Okay.
I'm lucky to have a distinctive last name. So my name is showing on the screen here.
Okay,
And
thank you.
Just Google that, possibly with the word mathematics adjoined, you will find me.
Okay, thank you.
Sure.
In Gordon and Netherlands paper, he has some, at the end of his paper, he has some proof of his main theorem. Then the correct term is the boundary slope of the checkerboard surface. Yeah, means the boundary slope of the checkerboard surface because the checkerboard surface is non-roundable. The equivalent the equivalence relation is actually corresponds to tube equivalent of the spanning surfaces. Yeah.
Yeah, but let me remind you that the theorem I prove in the notes requires actual equality of the Goeritz matrix. The thing that I was surprised by when I realized this was that the issue of congruence, of associating quadratic form, damages the integrity of the Goeritz matrix.
Yeah.
Okay,
You mean the congruence is not permitted? Yeah. Okay.
Right.
Okay. I understand. Thank
you. I'm right now. What I'm interested in is avoiding the mistake of presuming to understand the significance of the matrix by insisting on actual equality of the matrix. And that's where you get this vital connection with mutation.
So,
yes, I understand.
Lorenzo, you didn't say this, but isn't this matrix a linking form defined on the first homology of this surface?
Yes, and in fact, the invariance under conjugation of the congruence of the matrix, that P matrix P transpose stuff, that's what you do when you change a representation of an inner product from one basis to another.
I see. Okay.
So again, that's part of the machinery that doesn't have this vital link with mutation. That linking form is a weaker invariant than the matrix itself. The matrix itself has more information about the precise embedding of the diagram in the plane. And the linking form loses some of that information. So yes, it is the matrix of that. There's a good discussion of that in Licorice's textbook.
Right.
Now, I'm certainly not finding fault with that. I'm just saying that there's this level of detail that I wasn't aware of until recently, that the Goeritz matrix itself has information in it that is lost when you pass to the linking.
Oh, okay. Oh, okay. I see. Okay. Right.
The linking form is an invariant of mutation, but it is not a classifying invariant of mutation. You have non-mutant links with isomorphic linking form. Very easy to construct examples. In fact, the example I had that I mentioned in the paper, the connected sum of the two pretzels. Because the Goeritz matrices are equivalent under that conjugation, linking forms would be equivalent, but they're not, certainly not mutants because one of them is an unknown.
Are there any more queries or questions? No. Okay. Well, we're gonna have a little break now until September. We haven't got a renewal date. What do you think, Lou? We'll send around a note.
Yeah, I don't think we've decided exactly when we want to start again, but somewhere in mid-September probably.
Something like that.
You have to watch for the occurrence of some conferences.
Yeah. So
it's been great, guys.
Thank you to
Yeah, thank you very much to the two of you for organizing this. It's a real pleasure, this first batch.
it was fun doing it, wasn't it?
Yeah. Oh, and please remember to send your slides.
Oh, yeah.
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 I actually sent them to Roger already in case.
Okay, fine.
Yeah.
Right.
Okay, so it just remains to thank everybody. Being an audience is useful. That's a contributor. And then we'll try and get some sort of program going after we return. And if anybody wants to give a talk or about anything, just contact me or Lou.
Yeah.
I mean, I thought I might, something, you know, is a discipline would be to say, choose a subject you've always wanted to learn about, but you don't know anything, and then give a talk on it. Because that makes you learn.
A very dangerous strategy.
Yeah. Okay, so I'm going to stop now. I'm going to, I think Lou and Sam and Brian, we have a little chat. Chat. Yeah. Okay.
Do you want to just leave the Zoom on for that?
Yeah, provided everybody else goes.
He's kicking you out.
Bye.
Bye.
Bye now. Thanks. Very nice lecture.
Yeah, it was a good lecture. Yeah.
Very nice.
One of many. Right. 2 to go. Maybe they've.
As host, you may have a button that shuts the door.
I can eliminate them.
Yeah.
Remove. Okay. That's him and Abraham Sheikh. Remove. Oh, okay.
Power.
There we
are. A lot of power there.
Well,
Brian needs to turn his mic on.
Yeah, Brian, you need to.
Yeah, sorry, I got that.
Well, shall I start?
Sure.
What's your paper?
Oh, good. Okay. What I think is fairly self-explanatory. It's just a skeleton of something we could write up.
Oh, did you send a text?
Hello?
Yeah.
Hello, John Myers. You're a bit late.
While you speak to John, I'll be right back.
Okay. Hi,
Hi.
Hi. Aha. You know, you're an hour late.
Oh, okay. Sorry about that. Bye-bye.
Okay, but we have there's a recording which I'm now going to stop the recording.